Gödel's famous incompleteness theorem is unusual. It is an unprovability result that differs from traditional mathematical unprovability arguments in a striking way. In ordinary mathematics, when Standard proves that a statement is unprovable from a set of axioms by giving a model of the axioms in which it is false, right? Gödel's proof has a completely different character. It is a purely proof-theoretic argument that its statement is underivable. Given Gödel's other theorem that first-order logic and with identity also is complete, this does, of course, imply the existence of a non-standard model in which his statement is false. But the existence of this model is the corollary of the proof-theoretic argument, not the other way around. Notoriously, the argument involves self-reference, at least in an indirect way. There is another way in which the Gödel theorem might be thought to be unusual in logic. Really, some versions of the second incompleteness theorem, in a generalized sense, were already known and could be proved by obvious minimalization arguments. Consider von Neumann-Berneis Gödel set theory in Gödel's formulation, with or without local or global choice, right? Can one prove within this system that there is a transitive model M of the system, which is a set, right? The elements of the model will be the sets, and an appropriate family of subsets of the model will be the classes. See, this might be in some way proving its own consistency, that it has a standard model, so to speak, right? But this is, of course, impossible. If one can prove that there is such a model, there would have to be one with smallest possible von Neumann ordinal. That is, the order type of the ordinals, or equivalently the least ordinal not in the model, should be as small as possible. If this were provable within NBG, there has to be a model M prime in N, also a model of NBG. And this, of course, contradicts our assumption that the ordinal of M is as small as possible. One might prefer to refer to ZF or ZFC. Originally, I did so when I've given talks on this, but since these systems have infinitely many axioms and only finitely many need to be used in a given proof, it would be already unlikely and actually impossible to use them to get any model of full ZF or ZFC, and we don't need this other argument to show this, right? Yeah, okay. To get around this problem, I might imagine a finitely axiomatized version of ZF or ZFC with a rule of substitution in the replacement schema. This is the way one actually thinks of it anyway. Quine's virtual class notion could be used here. Then the natural proof will indeed have to be a minimalization argument. Presumably, this is what Kuratowski had in mind when he announced in the mid-1920s that the existence of a strongly inaccessible cardinal cannot be proved in set theory. Taking set theory to be FC, provability of a strongly inaccessible cardinal would imply that there is an R alpha, which is itself a model of the FC. But then, since R alpha is a model of the FC, there would have to be a beta less than alpha, such that beta is model of the FC. Iterating this would be an infinite, there would be an infinitely descending chain of ordinals beta, such that R beta is a model of the FC, which is impossible. Another case where a minimalization argument might be used is that if beta models of second order arithmetic, one cannot prove within second order arithmetic that it has a beta model. If this were possible, the beta model for smallest order type would have to contain a beta model of smaller order types, which is not true. Here too, there's a question about non-finite axiomatizability, which now there would obviously difficulties extending this type of argument to arbitrary models of set theory, arbitrary models, not necessarily well-founded models of set theory, or of ordinary number theory. In each case, given the completeness of first order logic, the consistency of the system is equivalent to the existence of such a model. The ordinals of an arbitrary model of CFC, say, need not be genuinely well ordered, so one cannot argue as we did before. And much less this is true of the customary first order arithmetic, where non-standard models are never well ordered. Nevertheless, I wish to find an argument for Gödel's theorem that could meet the following desiderata. One, it should have the form of a traditional model-theoretic unprovability argument. Two, it should not depend on Gödelian self-reference. Three, it should in some broad sense be a minimalization argument. Four, it should not be based on formal provability as opposed to a purely model-theoretic notion of consequence. So we'll slightly qualify this last desiderata below. Now, this argument will produce something weaker than Gödel's original, in that the statement proves to be unprovable to be pi02 rather than pi01. And to show that it is unprovable, we have to assume one consistency, that is sigma 01 correctness, rather than simple consistency as in Gödel's original proof. But it will have in common with Gödel's argument that produces a universal statement where each numerical instance is provable for each n, for each numeral if you are the n. But the universal generalization is itself unprovable. I will say also, I mean, this is not in the slide, that in a way, it will look like a consistency statement already, or something like a consistency statement. Here where I refer to provability, I mean model-theoretic consequence. So as I said before, this is okay. To show that the statement is undecidable rather than simply unprovable, Gödel had to assume one consistency. Actually, he says, omega consistency, one consistency suffices. In my own case, I need to assume two consistency for the same result. So of course, omega consistency more than suffices. Let us introduce the basic notions we will need. Consider statements in the customary language of first order arithmetic. This is formulated in first order logic with identity 0, plus, and times. The consequence relation is the usual one for first order logic with identity. We can think of statements as given in pre-next normal form with a strings of quantifiers alternately universal and existential, followed by a final formula with only bounded quantifiers. There is no loss in generality, assuming that the string of universal quantifiers comes first, though we will also allow the case with only bounded quantifiers added with no strings of universal and existential before. Consider a finite sequence, sigma 1 through sigma n, or an infinite sequence, sigma 1.
Sorry, I had to admit someone into it.
Sigma less than well, in infinite sequence as pictured. We assumed in both cases that for each I, if m and n are less than sigma I, then m plus n and m times n is less than sigma I plus 1. We now introduce a notion I call fulfillability. We define when a finite or infinite sequence fulfills a given statement as follows. If the statement has only bounded quantifiers, then a sequence fulfills a statement if and only if it's true. Otherwise, we can think of fulfillability in terms of a game where player 1 assigns values to the universal quantifiers, and player 2, sorry, I am not really assigns values to the existential quantifiers. Okay, go on. If the values assigned by player 1 up to a given play are less than sigma I, player 2 must respond with a string of values for the existential quantifiers less than sigma I plus 1, and so on. In the case of finite sequence sigma 1 through sigma n, we call n the length of sigma. If the sequence is finite, if length n, player 1 must always choose values less than sigma n minus 1. So player 2 has a chance to respond. If player 1 violates this condition, she loses. The same definition holds for fulfillability by infinite sequence, except that reference to the length of the sequence is eliminated. A finite or infinite sequence fulfills the sentence if player 2 has a winning strategy, that is, a strategy that guarantees ending in a true bounded quantifier statement. Note that fulfillability of a particular sentence by a particular finite sequence is always expressible as a delta 0, 0 sentence, a one involving only bounded quantifiers. For example, let A be for all x1, x2, there's a y1, y2, such as for all x3, x4. Here's a y3, y4, such that, okay, A of all those variables. Take the case where sigma is a finite increasing sequence of numbers. Sigma 1 less than to something less than L of sigma, which is the length of sigma. Sigma fulfills A if and only if, and here I've written everything out. For every I less than the length of sigma, and x1 less than sigma I, and x2 less than sigma I, then there exists a y1 less than sigma I plus 1. Remember, the existential player must choose from the very next sequence segment after the last one done by the universal player. Okay, there's the y1 less than sigma I1.
Yeah, let them absorb for a minute. And
What?
then let them absorb for a minute. And then...
Okay. Good.
Okay.
Okay, so Romina is assuming you read it all pretty quickly. Okay.
Go.
Notice that following Gödel, we're assuming that finite sequences of numbers can be coded as individual numbers. I mean, I don't know if a lot of use is being made of this actually. There are various ways of doing this, but I don't think that this is essential to Gödel's own original argument. This could not be done. We could think of statements expressible in weak second order logic, allowing quantification over arbitrary finite sequences numbers is primitive. Well, we won't go into this further. Note the following. Fact 1, A statement A is true in the standard model if and only if some infinite sequence fulfills A. Proof. If some infinite sequence fulfills a statement A, it clearly must be true, since the statement is implied by the strongest statement about the infinite sequencing, with the bound simply deleted. Conversely, if a statement A is true, we can define an infinite sequence signal fulfilling it simply by choosing the bounds for the existential quantifiers large enough to get the sequence to fulfill A, given the bounds for the universal quantifiers. Henceforth, we can confine ourselves to fulfillability by finite sequences, sigma 1 through sigma n. We call a statement n fulfillable if some sequence of length n fulfills it. The statement that we wish to prove unprovable is for a finitely axiomatized theory, which we may assume has a single axiom A. For all x, A is x fulfillable. For a theory with an infinite R set of axioms, A1 through AN, it is, for all x, the first x axioms of T are x fulfillable. Fact 2. If A is true, then for any n, A is n fulfillable. That is fulfillable by some sequence of length n. Once again, we can choose the bounds for the sequence so that it automatically fulfills the statement. But in this case, the converse of the statement does not hold. In fact, as long as every sigma 0, 1 consequent of A holds, the consequent of fact 2 also holds, since for any particular n, it is sigma 0, 1. However, even for a finite sequence, what is the case is that if one confines oneself to that sequence, then it looks as if A is satisfied in the sequence, since that is what it means to say that player 2 has the winning strategy. The only problem really is the restriction that player 1 must not choose too high. Fact 3, if a finite sequence fulfills a given sequence, so does any final segment of the sequence. Call a finite sequence good if its first member exceeds its length. Given fact 2, if for every n, A is infulfillable, then in fact for every n, some good sequence fulfills n. For if A is n fulfillable for every finite n, then it is actually 2n fulfillable for every finite n. And hence, the final n statements of the sequence of length 2n will have to be a good sequence fulfilling n. Let us assume that the axiomatic theory we are considering is strong enough to prove that any true sigma 0, 1 statement is strong enough to prove any true sigma 0, 1 statement, right? So like containing the theory R is enough for this. Now let's also assume this is a little bit stronger. Let's assume it's strong enough to prove fact 3. This is really dispensable in the argument, but as I'm giving it, it's needed. We can then assume that the n-fulfillability statement for every finite n implies that it must be n-fulfillable by a good statement. We can call this nicely n-fulfillable. In other presentations of this, I simply directly stated that this is what's independent, that is, for every n is A is nicely n fulfillable. then you don't need to go through something like fact 3. But then I noticed that in general, if the system is only moderately strong, right, we can actually show that the statement without the restriction is independent too. Okay. Here we are considering only systems formulated in the language of first-order arithmetic. Gödel wished his theorem, of course, to apply a system in richer language such as Kripke and Mathematica, okay, or ZF set theory, and so on. We can now rely on the fact that such systems have a number-theoretic part, either as primitive or by an interpretation. And the theorems of this number-theoretic part form a recursively enumerable set. Here is the one case where we do rely on the proof-theoretic notion of consequence. There may be some way of avoiding this. If so, it's probably due to Joseph Quincy and his thesis, but I have to look.
Joseph Quincy wrote a dissertation on this in 1980, and now it has been, retyped into LaTeX, and it's online. And he develops the notion of fulfillability, which applies to this, but also to some other things, right?
Other things,
it has
right,
other
yeah.
applications than the Gödel.
Oh, well, I have some of these other applications, but then, yeah.
Yes, I know.
But I mean,
but he develops those
he
too.
develops sort of other notions of fulfillability and so on. Okay. Okay, go on. In this case, the notion of certain axioms of theory is rather trivial, since there is no distinction between axioms and theorems of the system. Okay, since our theory is supposed to be correct and complete for all sigma 0, 1 statements, consider for each n the statement the first n axioms are all nicely and fulfillable. Now let us consider our model for the theory that is supposed to be, that is supposed to falsify the unprovable statement. We can call it a bounded ultrapower, that is, the elements of the model will be initial segments of an ultrapower. Consider a model indexed on the natural numbers, and we wish it to be factored out by a non-trivial ultrafilter. On the first coordinate, we consider a good sequence which is small as possible and fulfills the first axiom of T. By as small as possible, I simply mean with the smallest possible last element satisfying the given condition. In general, on the nth coordinate, it must be the smallest good sequence fulfilling the first n axioms of T. Such sequences must exist as long as the theory T is complete and correct for all sigma 0, 1 statements. Now, call the nth such finite sequence sigma n. So it's the nth sequence nicely fulfilling the statement or the nth statement. The first n statement says there are infinitely many. With its top element as small as possible. We consider the bounded ultrapower of all sequences bounded by each sequence sigma n, modulo any non-trivial ultrafilter on the positive integers. Note that by the goodness condition, the identity map or diagonal assigning n to the nth place is automatically included, right? The first element must be greater than the length of the sequence. Also, by the definition of n-fulfillability for each n, the sequences are closed under the plus and times operations. Remember that the theory T must be sigma 0, 1 correct and complete. Hence, for each particular n, the statement, the first n axioms of T are fulfilled by a good sequence is true. For any particular axiom A of T, eventually A must hold for sufficiently large n on each sequence of the bounded ultra power, since infinitely many coordinates must be in the ultra filter. This is because, well, so for sufficiently large n, the sequence automatically makes the restriction on player one be validated for any given particular sequences involved. And the idea that player two has the winning strategy will guarantee that A holds. Yeah, you have to look at it sort of coordinate wise, right? On anything. And coordinate wise, fulfillability will guarantee that the statement is true, right? On that coordinate. Recall we are not factoring out a non-trivial ultra filter here, so I said that. However, the consequence that for any n, the first 10 axioms trivially or nicely fulfillability, or even a special case where the identity sequence is put into this instance, cannot be true in the model. If it were, the minimality condition that each of our sequences, sigma n, is as small as possible, would be violated. So this gives us a model of n where the true consequence that the first n axioms of T are nicely n fulfillable for each n is violated. So QED, that is a Gödelian result, and the statement that cannot be proved is pi 0, 2. Okay. Another way of looking at it is this. Consider an arbitrary non-standard model of first-order arithmetic. If the statement that the first n axioms are nicely n-fulfillable is in fact true, then by the Robinson-Overkill principle, it must in fact be true for a non-standard element n, and indeed a smallest one, since this is definable in the model, so that it has a least element even in the non-standard element, right? This can be used to run through a smaller argument again, and yields as a corollary that any sigma 0 n consistent correct theory has a model on some initial segment of any non-standard model of arithmetic. It also yields a proof that first-order arithmetic or any of its consistent extensions has no finite axiomization. Here we can use the fact that for any particular A, the statement, if A, then for all XA is nicely X fulfillable, can be proved in first-order arithmetic. Okay, thanks.